Wait, stop for a second. I want to introduce this man to you. This gentleman right here is John Weilander. He's one of the leading Java-centric application security professionals on the planet. People ask me, who do I look at for research? And this man is one of my biggest heroes in the world of application security. He's a native of Stockholm. He's one of the greatest international security, application security representations in your country. You all should be proud to have this man as a member of your country. So, John Weilander.
So now can I introduce you, or should I just do the talk? I'm just kidding with you. This is a genuine application security hero, especially within the community of OWASP. How many of you have heard about OWASP? Oh, that is good. So the Open Web Application Security Project, Jim, he's been championing the cheat sheets where you can read up on how should I configure TLS or SSL and whatnot in application security. He does the OWASP podcast. He's a board member of OWASP. He travels globally to give training. And I think you even, your wife manages your flight schedule and rides around with you?
Well, she's like, you're going to Texas? Yeah, I'll pass. Well, you're going to Paris? Well, I think I'm going to have to go on that trip to keep an eye on you.
Yeah. So this is a true hero in application security. The floor is yours.
You're so kind, John. Thank you all for being here. Without further ado, let's get to it. So I'm mostly a server-side programmer, which means the design of my slides are freaking awful, and I'm okay with that. So that aside, hopefully the content is of value. JFocus 2014, top 10 security defenses for Java programmers, primarily server-side and web programmers, but hopefully even you mobile folks will get some value out of this. And so, yeah, JFocus, let's get to it. My name's Jim Manico. I'm on the board. I do some coding. I'm writing a book for McGraw-Hill at Oracle Press because I am a masochist and enjoy pain and suffering for less than minimum wage while being harassed daily by my editors. Yeah. So what kind of attack do we have here? Let's get right to security. Defensive programming 101. What kind of attack do we see on screen here? It looks so innocent. Single quote, semicolon. Big deal. But these two characters submitted legally into fields in your application can cause massive damage and havoc. What kind of attack is this?
Bobby tables.
Exactly. It's SQL injection straight up. I'm not going to spend too much time on this. Who here knows what SQL injection is and knows without any doubt exactly how you stop this vulnerability? Without any doubt. What's the answer? Go ahead, Dan. Yeah, it's right up there. This is a SQL injection attack, and the only proper defense to stop it is query parameterization, something we've had native in most every web-centric language as early as Perl. I'm going to go over this briefly because it's critical. I hope lots of you know about this, and if not, this is something we need to master to build secure applications. Here we have a simple feature. I'm editing a user account and submitting a new email address, and maybe you have a simple regular expression to allow a certain list of characters and deny others, but I'm going to try to attack this anyway. So this is a simple database query, update the user table, set the email to be the new email address where the ID is some trusted ID from session that identifies the current user who's executing this request. Now I have my super awesome advanced hack, single quote, semicolon. That's it. We take that single quote, semicolon, and frankly, those two characters are legal characters in an email address. So if your regular expression is just a list of blacklist characters to reject or a list of whitelist characters to accept, those will often slip through. So I put that in the email address. The quotes around the email address normally comes from the developer, and now we have a quote, single quote, a quote, semicolon in the middle of the email address, which is going to change the whole intent of this query. What does the semicolon do in any variant of SQL? It terminates the statement, so what the database sees is that. How is that going to affect your day as a developer of a web application, right? It's like update the users table and wipe out all the email address. I've seen this go live against a top Alexis 100 site and ended up taking it down immediately. Single quote, semicolon, game over. So we have to, the defenses a lot of security books talk about are input validation, perimeter defenses, and they're crap. We need to build our security to protect the individual layers of our code. So the closer our defense gets to the untrusted data, parser boundary, the better. What do I mean by untrusted data? User data is one of it, but you know what I think of untrusted data? Any variable, especially string variables, entering any subcomponent of my software. When you start to treat data as being tainted or untainted and make security decisions based on thinking a certain piece of data is safe, that almost always leads to failure. So when I look deep into securing like a SQL statement, I don't care what's trusted. In fact, I don't even care if it's a numeric. I'm going to apply proper defenses to all variables that enter subsystems of my software. When you think like that, you're building security in for the life of that software, not just for the situation that you're programming for. And don't make, because the shortcut you take today leads to data loss and worse tomorrow. This is a technique called query parameterization. You must master this technique when you're building a SQL statement, when you're calling a stored procedure, and in the stored procedure itself. A lot of people tell me, just use a stored procedure and SQL injection goes away, and that's a falsehood. You can have this kind of vulnerability anytime you're interacting with the database. Even NoSQL databases, graph databases, column databases all end up having some kind of string-based command, OQL, HQL, to retrieve complex data, and they're all injectable. So, query parameterization. We have our placeholders, question mark, question mark. We have our untrusted data with the set string binding into that query, and injection goes away. How does this work? Anybody want to offer something up? Besides Dan, how does this technique stop SQL injection so absolutely? Got to be a real deep database geek to know this. And in fact, I made a lot of my early speeches, I thought it was escaping at the Java driver. That made sense, and that's wrong. What happens is you're sending your query into the database essentially in two passes. First, you send the query in with the placeholders. The database will then build a query execution plan for that query structure. In the second pass, the untrusted data is sent in and runs through the query plan. The query plan is already built, so regardless of what attack is in your variables, it's not going to change the query plan, which messages the database how to retrieve and update data. Injection goes away. Your code looks a lot better than this huge string building of SQL, and you have performance benefits as your queries run faster because they're pre-compiled and cached in the query execution plan. And at the bottom here, anybody here use Hibernate or some object relational model in their work? So I've been told using Hibernate will solve all SQL injection automatically. That's not true. Now, if you're just using the criteria API of Hibernate, you are immune to SQL injection because the criteria API will auto-parameterize. But come on, how many folks build complex applications and did it all with criteria and never touched HQL? Anybody that absolute? There's a few, and you're crazy, because to really maintain the software, you're gonna want to build more maintainable software. I feel we have to move to HQL certain times. That's debatable, different talk, but even HQL is injectable. Same technique, emp ID placeholder, and then a bind statement to bind that variable into that placeholder. Query execution plan pre-compiles this. The structure of how to retrieve that data is locked in, and then the untrusted data goes in, and we don't care if there's an attack in it. We've protected that untrusted parser boundary, and our queries are safe. You've got to master this. If you're in a big company with lots of insecure applications, I recommend your first pass as you approach application security maturity, just fix all SQL injection everywhere. Because if you don't, it's like Aliens, game over. Ever see the movie Aliens? Who's seen the movie Aliens? Remember the scene where their main ship, their dropship gets destroyed? And the one guy starts freaking out, game over, man, game over. This is what SQL injection, he was talking about SQL injection. So password storage. Most of the new topic, password storage. Most of the advice you'll get about password storage is wrong. Plain text password stored in your database, game over. How about a hashing algorithm for passwords? The reason MD5 was created was to store your password one way, so it can't be reversed. What do you think of using a hash algorithm to store your users' passwords in your database to use later to check if they can log in successfully? Hashing algorithms? Anyone? Pardon me?
It's much better than clear text.
Yeah, clear text is obviously, that's almost criminally negligent if you're doing that. But a hashing algorithm is pretty much the same thing as plain text. when MD5 first came out in the early 90s, the idea of 10 terabytes of storage in your home was unheard of. It didn't even exist. Today, to get even like 1,000 terabytes in your home, you can actually afford that between cloud services or buying a lot of cheap drives and slapping together with open source software. So we can get a lot of terabytes at home to play with cheaply. That's what a rainbow table is. It's a pre-computed list of hashes. It takes many terabytes to build a good rainbow table, but now we can build a list of every possible password. It's a long list. And then get the hash, the SHA-1, SHA-2, MD5, Whirlpool hash of all of that. So it doesn't matter what hash you're using, secure hash or weak hash, it doesn't matter. It's always a bad idea to use a hashing algorithm to store a password because of pre-computed tables. So let me get right to the advice that I want to give you. I really want you to use an HMAC and cryptographic isolation to do password storage. And if you don't have the luxury of that kind of design and work, then I'm going to recommend an adaptive hash, a slow hash, or a slow algorithm like bcrypt or scrypt or pbkdf2 that's a reasonable choice to stop the threats we see against passwords, but it's going to be a denial of service vector as well. It's going to be a performance hit if you use these algorithms. Let's get to it. Number one, allow very complex and long passwords. Have you ever been to you went to a banking online site and you're a good developer and IT person, so you go and you give them a really complex password, but the bank says, whoa, wait a second. I know I'm protecting, all the wealth that you own, that you use to survive in the world, but you gave me a character, the single quote, I don't like that. Please give me a simpler password. Or wait, you just gave me a 50-character password. I know that we protect all of your hopes and dreams, but please give us an 8-character password to support our antiquated crap that we use to save your data. Anybody had that experience using an online website? Yeah, exactly. This is common. I apologize if you work for a bank, and no offense, man. It's just kidding around. And so a good system allows a user to use a password manager. Give me giant, long passwords with every possible character, even control characters, and I want to be able to handle it. That encourages users to use modern tools for passwords. Now, what's the problem with that? Anybody here heard of Django? Yes! No one's heard of it! No, keep your hand down. Because it's Python, and Python, of course, is a crap toy language that we don't want to use. So, I would never say that at a Python conference, but here, yeah. But, so, anybody here spend a lot of years working with Java, first of all? And have you ever gone from Java to try to play with Python for a bit? Is it an absolute, mind blank trying to do that? Just me? All right, moving on. So Django allowed unlimited size passwords and was using the PBKDF2 algorithm, password-based key derivation function 2. You can make that algorithm run really slow on purpose. I'll explain why in a second. And Django allowed unlimited size passwords. So an attacker threw like a 5 megabyte random password at Django, and it just pinned all the servers because a slow algorithm was trying to compute the key for that password. So we need to at least limit the size of a password, like 100 characters. So a really good password policy is force long passwords, allow large passwords of any character type. The longer, the better. When you look at the mathematics of password storage, the most important mathematical factor for password strength is the length of it. Now, regardless, passwords are a bad idea. More on that later as well. So number one, allow big complex characters. Number two, use assault. Why? First of all, what's assault? All that assault is, it's a random string that we're going to attach uniquely to every user account. So every user in the user table will have a separate random string for their assault. I like to use 32 characters minimum. And the purpose of this, and we just add it to the password before we use some protection algorithm. The purpose of salting is twofold. Number one, it defeats most rainbow tables. Remember, a rainbow table is a pre-computed list of hashes. Attackers don't even use them anymore, but it's still important. And the point is, if we add this random string to a password and then protect it, the password's essentially more than 32 characters in length. And to store every possible password up to 32 characters, there's not enough storage in the world to do that today. So that's why we use assault, to get rid of pre-computed lists, but also deduplication of passwords. Now remember, the whole purpose of this section is I'm talking about password storage to protect you when failure happens, when your database is stolen or SQL injection steals your data and the attacker has all your password storage data. How is that going to affect your system? If it's plain text, it's game over. If it's a hash, it's game over too, frankly. LinkedIn, no offense, LinkedIn was hacked about a year and a half ago. They were using MD5, and 90+% of users' passwords were reversed to the plain text password within the hour of that list being released. That's how bad a hash is for password storage. Salting makes it a little bit stronger because even if you and I have the same password, we're going to have different ciphertext. Let me explain this. If you don't do salting and I steal your database, I can go and use your protection algorithm to make a ciphertext of that password and in one pass compare it against everyone in the whole database in one shot. So that's duplication of passwords is a problem there. Sir, I'm going to guess your password. It's the same as mine. Fluffy Bunny 1, exclamation point. Am I right? So if we had that, if in our database, if we just use a hash or even these stronger algorithms, our ciphertext will be the same. So I can just try Fluffy Bunny 1, get that ciphertext, try it against everyone, and see who matches, and I have all their passwords. So the salting, unique to every user account, will deduplicate even people with the same passwords. So this is basic. We're still basic. So regardless of what algorithm you use for password storage, use salting, a unique random string per user. Next, and this is the best way to do password storage. It is a little bit tricky for engineering, and it's not a slow algorithm, it's not a hash, it's not even a key derivation function, it's an HMAC. HMACs are cool. This is an authenticated hash, a message authentication code. A hash, you just give it a string, and you get the hash value. An HMAC requires a private key. So I'll give the HMAC my private key, which I got to protect in secret. Then I'll give it the salt and password. And what will come out is the HMAC hash. Now, the benefit of this algorithm is it's just a hash primitive, so it's super fast. It scales. But you have to protect that private key well. How difficult is protecting private keys in the Java ecosystem? If you're going to do cryptography and you got private keys, the keys to your kingdom, how do you store those private keys? It's a very difficult problem. We might use a key storage. We might use a hardware security module and request that key in the web server itself. That's what many people do, and it's a terribly bad idea. Anytime your software, your application web software is talking to a private key, I respectfully say you failed to do cryptography right. The keys should be isolated in a vault, and your system should never be exposed to those keys for web services and web application programming. You want to isolate that crypto to a separate service. This is more important than key management. In fact, when I describe how to do an HMAC, you can even hard code the key in the web service. It'll be more secure than doing this function in the application itself where you're retrieving a key from a key storage device. So what I recommend is you build a separate service. And all that this service does is it takes a string and spits out a hash. There's no logging into it. There's no other access to it. It's just a simple password hash generator. So in comes the string, password and salt. And then inside of that service, we'll grab the private key, drop it in the HMAC, do the HMAC computation, and spit out the hash. That way, even if your web server is attacked, your database is stolen, your configuration files are stolen, this service is locked down and protected, and the private key that drives all your passwords is still protected. And if that key is long enough, and the attacker steals all the HMAC hashes, they're not going to be able to reverse it before the sun stops working. And I'm not kidding when I say that. That's real cryptography. So this is a HMAC. Isolate the process in a separate service. That should take you like 3 hours to build. It's a very simple service. And now you have ultra hardcore password storage. Now, if that service gets compromised, your whole system's compromised. But we can isolate that well to make it very difficult to attack. So this is ideal. It's still a reasonable amount of engineering and architectural changes to make it happen. So let's suppose you want to make a quick decision, but still make at least a reasonably good quick decision for password storage. Then I recommend PBKDF2, scrypt, or bcrypt. These are one-way or key derivation functions that are really slow on purpose. Why would I want to do an algorithm That's really slow on purpose. Have any of you been told in your career, sir, your code is running so fast and efficient, we have a problem with that. Can you please slow that down and take up more memory and make sure you're using more CPU? Ever been told that in your career? But for password storage, it's not unreasonable advice, especially for systems that don't require great scale. Like if you're building a credit card vault system where only one admin at a time will use that system, using a very rigorous, slow algorithm is actually not a bad choice. So PBKDF2, it's a password-based key derivation function 2, available native in most languages. You give it the salt and password, you give it a work factor to slow it down, and it gives you back a key that you can store for that user. The reason you want to use a slow algorithm is because attackers don't even use rainbow tables anymore. They'll just throw like a video game machine at you, slap a whole bunch of video game cards in, put Linux on it, and now we can do like at home, after we've stolen your database, we can do like 100 billion hash attempts per day? Per hour? No, per second. 100 billion hashes per second to try to crack your system using about 5,000 euros worth of hardware. And that's only going to increase with Moore's law. So attackers have supercomputers, so these slow algorithms help defeat brute force attacks, dictionary attacks against your stored data, against your stored system. So let's charge on. Cross-site scripting. This is a prolific problem in Java because the Java ecosystem has almost nothing tool-wise to help us stop cross-site scripting. We need a pretty rigorous web-centric encoding library as our main line of defense, and the Spring library is inadequate. It's not complete. Doesn't even exist in core Java. The J2EE team is going to build this in maybe in a few versions down the road. So there's really nothing good in the core of the Java ecosystem to provide you defense here. And so I'll show you some open source libraries members of OWASP have built that I feel are very much production quality to help stop this risk. So cross-site scripting, back to the beginning. We're all logged in on Swedish Meatball Chat Roulette, a website that I'm working on. And so we're all logged in and authenticated, and we're chat rouletting and talking about Swedish meatballs. Awesome. So if we're all logged in, what happens if I steal your cookie? In your cookie is your session ID. If I can grab your session ID, I can't log in as you, but I can compromise your currently logged in account and hijack your account. So this attack here, I post to chat roulette, you read this message, and the website's insecure, so it just executes this script. And this script redirects you to my evil website. We grab the cookie, attach it to the URL, and then you're going to walk in front of me in the middle of the presentation? Really? I'll get water. I'll go for it. Here. No, I'm with you. So, would you like some water? Oh, you really are walking in front in the middle of the presentation. Bafangu. Okay. I'm Sicilian, by the way. I'm Sicilian, and I live in Hawaii. That's why I'm dressed like a fool, so aloha. All right. So here we go. Window.location. So we're chatting together. You get this attack. It redirects you to an evil website that I control, but we also attach the cookie to that URL before the resubmission. So now when I look at my log files on my evil web server, I see you making a GET request with your session ID in it, which I can grab and hijack your account. The second one is really simple site defacement. But really, once I can get JavaScript as an attacker, when I can slip JavaScript in and have the victim read that JavaScript, the things I can do are off the chart. I have full control of the web page. Session hijacking, deface the website for that user. I can undermine other defenses. I can redirect the user, steal any data from the web page, set up a keystroke logger in JavaScript, and attackers are using this more and more frequently. How do you stop cross-site scripting? What do you think? How do we stop this kind of attack in our web application? Input validation's one of it, but that's a bad defense to depend upon. Here's why. Suppose you have a news article and you're allowing an open comments field so we can chat back and forth in natural language. What characters should we be accepting? Uppercase letters, lowercase letters, a lot more for internationalization, spaces, most punctuation, and guess what? That's all I need to conduct cross-site scripting. So we cannot depend on input validation to stop this risk. It helps reduce the attack surface, but it does not eliminate the underlying problem. So input validation, every secure coding book I talk about says that's the solution to cross-site scripting, and they're all wrong. So let's get to it. To really stop cross-site scripting, to avoid script injection from the attacker in your browser, you need a multitude of different defense strategies, which makes this risk actually rather difficult to stop. Depending on the context of where we're putting data in the web page, we want to escape it and convert it from a code context to just display data context. Or suppose someone's submitting untrusted HTML to our website for some rich text editor. Then encoding won't help us. We need to do HTML sanitization. Or what if we're using a dangerous API in JavaScript like inner HTML? We should redesign and avoid it. So the actual real defense to stop XSS, that knowledge, the grammar to apply those defenses are radically complicated. Michael Samuel from Google is actually building a metagrammar to explain these defenses in a meta language that can be applied to all other languages and templates to provide auto-escaping and defense. So bear with me. What happens when you're in the body of your HTML document and the HTML rendering engine sees this character? What does the browser think you're doing? How does a browser treat this character in the body of an HTML document? It's starting a tag. This is not display data to a browser. This is code to a browser. So how can I render this character in the browser, in the body of HTML, in a way where it's display data and not code? What is it? You're there. What, 4 characters. What are they? Ampersand? LT. Ampersand LT semicolon. This is an HTML entity. When the browser sees this, it displays the less than sign without triggering the markup rendering engine. So the problem, though, is we put untrusted data in so many slots in an HTML document. JavaScript variable assignment, cascading style sheet value, the body of HTML, in an attribute. We put it all over the place. And every slot in an HTML document will require a different kind of escaping. Introduce the OWASP Java encoder project. It is a high performance, meant for scale, low memory utilization, and high CPUs, low CPU, low memory, high speed utilization, really is written by a PhD student who studied all the different browser rendering engines to minimize what characters need to be encoded. We keep this, it's very active. We just dropped a new version yesterday while at JFocus to fix a few bugs and provide integration with other security libraries. And there's a granular encoding function for pretty much every possible slot in an HTML document. Well, you'll put a variable or untrusted data. And so this is complicated. I'm going to show you a couple, and each individual one is not complicated, but getting this right at scale across a large organization is a brutally difficult management problem, not to mention legacy software, going back and fixing it, where we depend upon untrusted data driving certain functions because of bad design. This can be difficult to use. So let me give you a couple examples, and these are hopefully some straightforward ones. We have here the top one, we're putting untrusted data in a quoted attribute in HTML. So I'm going to say encode for HTML attribute with that untrusted data value. The second example, I'm populating a text area with untrusted data. So I'll say encode for HTML content. The third one, I have a button on click handler where I have an alert. So I'm already in JavaScript space when I put my untrusted message into that variable. And that's encode for JavaScript attribute. And the next one, I'm putting untrusted data in a script block, doing a JavaScript variable assignment with potentially untrusted data. So I say encode for JavaScript block. When I look at my JSPs or other user interfaces and I see all these variables populating the page, I don't care where those variables came from. I encode all of them. And now my user interface is fully injection resistant regardless of what's happening upstream. That's how you build secure software, in my opinion. So here's another edge case example. I think it's kind of cool. I give Jeff a lot of credit at how much research he put into this library. They use it at SuccessFactors, which requires incredibly massive scale, and it stands the test of time. Here he's dynamically building a block of JavaScript server side. This is actually a URL to like a dynamic .js file, basically. It's a different kind of encoding. Encode for JavaScript source in the alert. It's a different kind of encoding because it's a server-side JS resource, not embedded JS resource. And you don't need to master all of these encoding functions. You can just use the top function of each family. It's a little less performant, but it's easier to use. The reason why Jeff wrote such a granular API, he wants template authors, people who are building the next version of JSP, to integrate this into their libraries so they auto-escape, so we don't have to do it as developers. So that's the goal. If you're using struts or Spring or Wicket, many of the default components will do this escaping for you. But as soon as you start building your own unique components or you start doing heavy JavaScript work, no Java framework provides defenses for that kind of work today. We need these manual escaping functions when building components. So, woohoo. So next, the other part of XSS is, what if we're dealing with untrusted HTML? We deal with untrusted HTML all the time. So HTML sanitization will take untrusted markup as input and make it safe, output it safe so we can render it safely for other users. And we can't encode. What if we take a big chunk of third-party HTML and encode it before we put it on a web page? What will we see on the web page? We will see the HTML. We won't see the design, we'll just see the HTML. And it will be safe. It won't cause cross-site scripting, but it will break the whole functional purpose of using a WYSIWYG editor. So let me show you what I mean by this. Here's a tool, TinyMCE, one of the more common WYSIWYG editors used for web applications. You can do bullets and embed images and bold and colors, you name it, you can do it. And when you submit that, it submits a big chunk of HTML to your server. So riddle me this. What can I do at scale to grab a chunk of untrusted HTML and assure it's safe and has no evil JavaScript in it? What do you think? How do we solve this problem? Should we use a regular expression to parse arbitrary HTML and sanitize it? Anybody think that's a good idea? Sorry, that's not. Guns are bad here. I'm sorry. That's good. I meant flowers. There we go. So there's no good defense built into Java to do this. We need a third-party library. My favorite is the OWASP HTML Sanitizer project. Michael Samuel, the lead application security architect from Google, saw how we were doing HTML sanitization at OWASP with a project called Anti-SAMI. He had a counter to that project. Anti-SAMI is a good project. I'm more of a fan of this one. This is a highly performant, high-speed, low RAM, low memory, and low CPU utilization HTML sanitization library. It is trivial to use. It's server-side programmatic configuration, and it's meant to take arbitrary HTML, make it well-formed, and run it against a policy so we eliminate certain content that could be untrusted. Here's an example of how to use it. We're building a policy factory. We're allowing A tags with HTTPS links only. We're allowing the href attribute only, and we're not allowing relative links. Now we have our policy, and then we say, sanitize with our untrusted HTML, and what comes out is something we can safely render to any user. We can use this against advertisements. We can use this for tiny MCE use cases. The need to do HTML sanitization comes up more and more. You're better off using something like Markdown, but we have a lot of legacy need for this kind of function. And Google uses it at great scale successfully, so excellent. And here's an example of a more complex policy. I'm allowing certain styles, I'm allowing certain header tags, and I've defined my policy. I give it untrusted HTML. Whatever comes out of that sanitization is safe, at least it follows that policy and is safe to render to other users. Actively maintained by one expert. Here's the debate. We see something like ISAPI in the OWASP world maintained by a group of folks of mixed skill of developers. And we have something like these other granular libraries which are maintained by one deep security and developer expert. I feel that that's the better way to go. Get one genius to build that library and maintain it, and let's all use that as a component for secure software. Next, we have a bad design. Let's fix this slide. So I had to port this from a different presentation. It's a live edit. It's an exciting moment. We're feeling it. We're feeling it. So now we have cross-site request forgery. So if we're looking, note we're on evil.com. We're on an evil website. So when we're on evil.com, what's going to happen with these image tags? The first one is image source is the logo from Google, but it's not being hosted. This page is being hosted on an evil website, not at Google. Will that image request work? Can I load an image from another website, from a different website? Is that acceptable? In every browser since Mosaic, this is an acceptable thing. The image tag has no origin policy. Image tag by default lets you make a request to any other server. What about this next one? HTTPS, google.com, delete mail 7, confirm is true. I'm making that feature up. If I was logged into Google and I'm hosting this request on evil.com, what kind of request does that image tag make, first of all? It's an HTTP GET. Will that include my session cookie? Yes, it will. So now I can host an image tag with no size, make it invisible, or do it in JavaScript on a third-party site that makes authenticated requests to other sites you're logged into. Cross-site request forgery, right on. Before I forget, the whole password storage section, all that research came from John Steven at Cigital. John, you're awesome. Thank you for your help there. Moving on, back to cross-site scripting. So what about the third one? Someone told me if you just make everything a form, you're safe from CSRF because we can't fake a post from an evil website. Well, I'm doing it right here. I have a form. I just build a form. It's going to post to the bank. It's going to make a banking transfer, and I'll just use JavaScript to submit that post. All of these will work and potentially will cause damage. We've seen this at Netflix. Very quickly, if you're logged into Netflix and you visit this evil web page, look, start at the body tag. Body, we have an image, no origin policy. It makes a request to Netflix. Add to queue, movie 701106772. The height is height and width are 1 pixel. We can't even see this. But if you're logged into Netflix, it's now making authenticated requests out to Netflix to add a movie to your queue. Now this goes to the bottom of your queue. Then we call the script, set timeout, wait 2 seconds, load image 2, which is defined in the header, which says move to top, movie 701106772. And now, without knowing it, you just took a movie. It's now the next movie to show up in your queue. And this was actually at the time this attack happened, that was the closest Netflix had to pornographic movies, and it got sent out to a lot of people. And you know, us Americans were a little puritanical, you know. Okay. We saw Twitter get hit by this. On Twitter, in Sweden, it'd be like, oh, look at the movie, give it to the kids. Go ahead. All right, no, I'm just kidding. So here we saw that Twitter had a good cross-site request forgery defense. They were using a synchronizer token. And so here's a little script that got snuck into a tweet, would grab a copy of the page, do a JavaScript call, rip the token out of the page, and then replay that token and circumvent the XSS and CSRF defense of this web page. And this is called the goat worm. And actually, all of a sudden, like hundreds of thousands of people on Twitter were expressing their deep love of goats. And hey, no offense if you're into goats, you know, it's whatever works for you. But so now this should concern you, because we can also use cross-site request forgery to compromise private websites or a home router in this case. So if I'm here right now, I have no ability to hit the administration console of your home router wherever you live in Sweden or whatnot. But if I can get you to visit this web page, this will execute in the browser while you're at home. And then look at the form action, 192.168.1.1. That's your home router. And this is an older router. This is actually a real-world attack in Brazil where everybody pretty much had the same home router, had the same telecom. This would change the password to a known password by the attacker. The attacker could then root the router and just log into the router with that root password because they forced the user to change it. Again, the form action is your local password change feature of your home router. It's a weak web application that doesn't require your original password. We just say change password, and bang, Now the attacker can trick you into making any configuration change on your home router. And what this attack did was the attacker would change your DNS entry in your home router, so when you went to visit your national bank, you went to a phishing site as well. It'll pop up SSL certificate warning, which most people go, no problem, and then give the attacker their password. The way you solve this problem is with the combination of cross-site request tokens, re-authentication. All right, John, I'll say it, or the double submit cookie defense. I don't like it, but it's really hard to pop. So I don't talk about it here, but I just went and added a lot of your slides to my presentation, so I'm in. It is a reasonable defense. More on that later. So the main defense is the synchronizer token pattern. When the user first logs on to your web application, use a new instance of the secure random class to build a large random number, hash it, and then save that in the session. Now we have a good large random string. Whenever you're building a form or a sensitive feature for that user, you take that token from session, which is unique for every user. It's even unique for you. If you log off and log on, new random string. We take that random string, add it as a hidden variable to all of our sensitive forms, every sensitive form, and when someone submits a sensitive request to your server, we rip out that token from the hidden variable, compare it to what's in the session. If they don't match, reject it. And I don't use the session ID for this. I use a whole different random token for this for a variety of different reasons. This is called the synchronizer token pattern. Spring integrated this a few months ago. Struts has had it for a while. And you want to rigorously test to make sure your framework is doing it well. And so another defense against CSRF is re-authentication. Whenever the user is trying to change a password, conduct a significant banking transfer, or trying to change their email address, you should force them to re-authenticate. Even when they're changing their email address. Most websites actually don't do this. Why would I want to make a user re-authenticate just because they're changing their email address? What's the big deal? Most password resets are built very weakly and only depend upon an email reset link. This is a bad idea, but that's what most people do. So if I can change your email address, I have your whole, I'll change it to an address I own as an attacker, and I have compromised your whole account. And so Meetup, Amazon, Facebook, the pillar of insecurity, and even and Twitter, all of these sites force re-authentication when you're trying to change your email address. It's a good defensive call. You should do it as well. So cryptographic storage. If we want to store sensitive data, new topic. We want to store sensitive data in our database or in the application in some way. We should use AES, right? But can we just use Java to call AES and we're good to go? No way. We have to use AES. We want to avoid ECB mode, the default Java mode, which is basically plain text. We want to use glossy encounter mode, which is an authenticated encryption, which isn't widely supported, so we're stuck with AES CBC. We want to have a unique IV per message and proper padding, key storage and management. We want to also do confidentiality. When you encrypt data, you only get secrecy. You don't get integrity as well. So if we want integrity, we want to HMAC the ciphertext to get that integrity, and we should derive integrity and confidentiality. We want to derive integrity and confidentiality keys separately from the same master key with labeling, and don't forget to generate your master key from a good random source, and good luck with that. Right? So we don't want to do this ourselves. We will fail. The best cryptographers in the world get this stuff wrong. So let's use a library, and the only good crypto library in the Java ecosystem, I say with respect, is Google Kezar. It is completely open source. It does things like key rotation. It does all the proper modes of encryption. All the difficult things are encapsulated in this library. Sure, it's had problems, but it's the best out there. I would standardize on this for my cryptographic storage needs, and I would isolate my cryptography to a separate service. When I do that, I reduce the problem from crypto to access control. Let's move on. Clickjacking. So when you see this website, what are you thinking? Doctor, I know what you're thinking. You're thinking, Jim, I've got to play some super fun games. I am with you. So we go hit this website. It's an evil website, super fun game. So we hit one player, start game. Now, unbeknown to you, and Doctor, are you logged into Gmail right now? Say yes. Yeah. Oh, I'm sorry to hear that. So when you go and visit this evil website, we can then pop Gmail in an iframe. Now, the evil website can't read your email when you do this. The evil website can't see your cookies and steal your account, but it can force you to pop your inbox. And now I can take that frame and change the style. I'll give it a specific height and width. I'll make it opacity 0. What does a 0 opacity do? Now, it makes it invisible, but can I still click on it? Yep. Exactly. When you use CSS hidden, it goes away. It's no longer interactable. But a lot of rich applications in the web do this. They'll make a component with an invisible opacity, so it will trap clicks on a web page in a certain way. Now, I'm sorry, sir?
For styling file inputs, they use that.
Yeah, for styling lots. Exactly. Now, the problem with this is, well, as the attacker, when I make this iframe invisible, it's invisible but clickable. So let's go back to super fun games, hacker style. So, Doctor, could you click one player for me? Just from right there. Ready? One. Everyone look at one player. Right in the middle of it. Let's go click it. 1, 2, 3, click. Ooh, select all. Let's click on start game. You ready? 1, 2, 3, with me. Ready? 1, 2, 3, click. Ooh, delete. Welcome to clickjacking. How do you stop this? With X-frame option headers. This is trivial. Add a response header when you're delivering a web page that you do not want evil websites or third-party websites to frame. Use X-frame option, same origin. It's a simple response header. It will block third-party sites from framing your web page, but still let your own domain to frame it for your own functionality need. There's even legacy browser clickjacking defense. If you want to support older browsers that don't support X-frame option, go Google Code Magi defense, and you'll have this. And I'll give you a link to this deck. This is an open deck to use as you see fit. Next, access control. How much time do I have, John?
5 minutes.
5 minutes. I'm going to go fast. Role-based access control. Our back is an anti-pattern. Ever see code like this? If the user's a manager, or if the user's administrator, or if the user's an editor, or if you're born in Sagittarius, then let them do that, right? This is how most of us code access control, and it's an anti-pattern because it's hard coding policy in code. If you forget to add the policy, usually you're open by default. It just doesn't support horizontal data contextual access control. RBAC is dead. Stop using it. We want to use capabilities access control or ABAC, activity-based access control, which NIST just released the new standard at about a week ago. So here's Apache Shiro. The quality of Shiro is debatable for some. A lot of people complain that there's a lot of work up front to configure the policy. That's the case in any good access control system. So Apache Shiro has built good capabilities access control from the ground up. What I would normally say in this video game is, I want to see if the user can wield a lightsaber, if the user is a Jedi, or if the user is a Padawan, or if the user is a Sith Lord, or if a user is General Grievous, the Jedi-killing robot. He's not a Jedi, he's not a Sith, he's a human who's a droid, who is human, who's a cyborg, who was trained by General Sidious to defeat Jedis in lightsaber combat, so he's a unique identity. And so that role system will always have to manipulate it over and over again as we change the policy. Instead, let's check the activity. If the user is permitted to wield a lightsaber, and under is permitted, we'll build a good data model to do these checks. So that way, when you have these kind of calls in 10,000 places in your application, you code it once, you'll never have to touch it again. You just modify the policy in the back-end system. Here's another way of looking at it. This is a horizontal access control request here. We're grabbing, the user's trying to see if they're allowed to drive this Winnebago from the movie Spaceballs. Important movie watching. We grab the object we're trying to manipulate, the ID from the request, and we say, if the user is permitted to drive Winnebago of that number, we let him do it. We code it once. Even if our policy changes, we'll never have to change our code again. And this kind of mechanism handles contextual access control for data-specific access control. A quick thing for intrusion detection. Think of a drop-down list, a drop-down menu of country codes. Is it possible for a user to submit anything but that list of country codes to your server? No, it's not, unless they're abusing your web application. So on the server, when I'm checking a select list choice, I say, if the choice is in the list of items, then good. If the choice does not match my list of items, it's an attacker, and immediately lock their account and call and contact our administrator to take action. From one failure only. And this is a great way to stop an attacker incredibly early on. Think of all of your immutable form components. Radio, checkbox groups, radio button groups, select menus, multi-select lists, and hidden variables. All of those should not be ever modifiable by a user using your application in a good way. Attacker can proxy it and tamper, and if we can detect that on the server with very easy code, lock the account right away, and we have some really impressive intrusion prevention and intrusion detection in our code. HTTPS, we have a couple, I have like, how much time do I have, John?
About 1 minute.
About 1 minute. It is possible for certificate authorities who have sold their private certificate of their authority to public companies to man the middle U without browser warnings. So we want to make sure that the certificate the server gives us for SSL matches what we've hard-coded in the app. That's called certificate pitting. Mobile applications, thick client applications, Android on Android, Chrome on Android, and pretty soon browsers will all let you pin the certificate so they can detect when a CA valid but invalid certificate's been sent to your browser. Multi-factor authentication, passwords are dead. They're awful. Stop using them. Offer multi-factor for all of your web applications moving forward that you care about security. And with that, I am done. I really appreciate your time. This presentation is all open source. I encourage you to grab it, pretend it's yours, put your name on it, plagiarize it, and spread the word about application security. The lack of security is challenging the cohesion of the whole world today. It's eclipsed global drug trade. I care about the world knowing about this before anything else. Take it, spread the word. Thank you for your time. Go write secure code. Cheers.
Great of you to come here, Jim, and I think it's time for a coffee break.